Hello, welcome to the second part of the Advanced Calculus mini lecture on how to model multivariable functions from real-world examples and how to use such functions for optimization. I hope you covered absolute optimization of multivariable functions and optimization with constraints using Lagrange multipliers in the meantime. These two techniques are needed. Let me briefly review what we discussed in the first part of the mini lecture. We used the following open box example. An open box should be constructed. The cost for the bottom is $5 per square meter. The cost for the left and right is $3 per square meter. The cost for the front and back side is $2 per square meter. There is also a restriction. You have to use $20 for the box. The tasks were 1. Express the volume of the box in terms of the dimensions of the base. And 2. Find the dimensions of such a box that maximizes the volume. Task 1 was finished in part 1. Task 2 will be discussed here. Throughout we use x for the width, y for the depth, and z for the height of such a box. Maybe I should give you 30 seconds here in order to allow you to guess the solution. Maybe not the values, but the relation between x, y, and z. Should all three values be about the same? In other words, should the box be a cube? And if not, which one of the three values should be the largest? Let's first solve the problem using global optimization. In the first part of the lecture we found that the target variable volume depends on the two choice variables x, the width, and y, the depth, as follows. f of xy, the volume, equals xy times 20 minus 5xy divided by 6y plus 4x, and this can be simplified into 20xy minus 5x squared y squared divided by 6y plus 4x. Here are the level curves of the function. From them we can already see that the maximum is around x about 1.4 and y about 0.9. How can we find the values x and y that maximize this function f without the graph, or how can we get them precisely? Well, we need the partial derivatives. Using quotient rule we get the two partial derivatives of f. Now we need a little algebra, simplifying algebraic expressions, factoring and expanding. The numerator of the first expression has a common factor of 10y, which we can pull out. In the same way, the numerator of the second expression has a common factor of 10x. We expand these expressions, we FOIL or use distributive law. Then in each case, two of the terms vanish and we can simplify as follows. First for x, foiling and distributing, and then two terms vanish. Now for y, foiling and distributing, and two terms vanish. Then we can factor a little more, having a common factor of 2y in the four terms of the first expression and a common factor of x in the four terms of the second expression. So we get this. And that. Now the critical points are where both partial derivatives are equal to 0. That means that their numerators must be equal to 0, so we get y squared times 6 minus 3xy minus x squared equals 0, and x squared times 8 minus 4xy minus 3y squared equals 0. Since boxes with no width or no depth do not have any volume, so x equals 0 or y equals 0 does not lead to a maximum volume. So we get 6 minus 3xy minus x squared equals 0, and 8 minus 4xy minus 3y squared equals 0. The rest is algebra. Two nonlinear equations with two variables, substitution method, clearing the fractions of a rational equation, resulting in a quartic equation that is in fact a hidden quadratic one and can be solved using quadratic formula. Almost all of it is basic college algebra stuff. Please check back there if you feel insecure here. We solve the first equation for y and get y equals 6 minus x squared divided by 3x. When we plug this into the second equation, we get this equation here, or distributed or simplified x squared plus 4 minus 12 over x squared equals 0, a rational equation. We multiply by x squared and get the following quartic equation, x to the power 4 plus 4x squared minus 12 equals 0, which however is a hidden quadratic one. We can use the substitution u equals x squared and use quadratic formula for the resulting quadratic equation in u, which is u squared plus 4u minus 12 equals 0. So we get u equals negative 6 or 2, or x squared equals negative 6 or 2. But x squared equals negative 6 has no real solution, and x squared equals 2 has only one positive real solution. X equals square root of 2, about 1.414. Then our substitution equation y equals 6 minus x squared over 3x used above implies y equals 4 over 3 times square root of 2, which is 2/3 square root of 2, which is about 0.943. Moreover, the volume is the f value for these two numbers, square root of 2, 2/3 square root of 2, which is 10 over 9 square root of 2, which is about 1.571. This is indeed the maximum possible volume we can get. Let's now move to the second approach, optimization with constraint using Lagrange multipliers. We discussed this approach in the first part of the lecture. We formulated the problem as maximize the volume v of xyc equals x times y times c, given the constraint 5xy plus 6yc plus 4xc equals 20. Let's again show the surface of the restriction together with one level surface of the volume function v. The level surface of v is the one with the red border. Both these surfaces touch at one point, which is the optimum. We know that in the optimum the gradient of the function g of xyc, which is 5xy plus 6yc plus 4xc, which has our restriction equation as one of its level surfaces, and the gradient of this function v must be parallel. These gradients are as follows. The gradient of g has components 5y plus 4c, 5x plus 6c, and 6y plus 4x, and the gradient of v has components yc, xc, and xy. Therefore, the gradients being parallel, the gradient of v must be a multiple of gradient of g, so gradient of v equals lambda gradient of g for some lambda. We have three equations, one for each component. The fourth equation is a restriction g of xyc, which is 5xy plus 6yc plus 4xc, equals 20. So we have a system of four equations with four variables x, y, c, and lambda. We may use substitution method to solve this system. First, we solve the first equation for lambda as lambda equals yc divided by 5y plus 4c. Then we plug this into the other equations and get xc equals this expression times 5x plus 6c, and xy equals, well, expression for lambda times 6y plus 4x, and the last equation remains unchanged. We multiply the first equation by 5y plus 4c and get 5xyc plus 4xc squared equals 5xyc plus 6yc squared, or 4xc squared equals 6yc squared, or 4x equals 6y, y equals 2/3 x, under the natural assumption c not equal to 0. We do essentially the same for the second equation. We multiply by 5y plus 4c and get 5xy squared plus 4xyc equals 6y squared c plus 4xyc, or 5xy squared equals 6y squared c, or 5x equals 6c under the natural assumption y not equal to 0, or c equals 5 over 6 times x. So now we have expressed both y and c in terms of x. We plug this into the last equation and get this equation here, or that equation there, which means we get 10x squared equals 20, x squared equals 2, x equals square root of 2. So again we get x equals square root of 2, which is about 1.414, y equals 2/3 of square root of 2, which is about 0.943, c equals 5 over 6 times square root of 2, which is about 1.179, and for the volume we get v equals x times y times c. We plug the three values in and get 10 over 9 square root of 2. Everything is in the previous approach, of course. The width x is largest, followed by height c and depth y. Isn't the reason obvious? The bottom is at $5 per square meter, the most expensive part, but since we have two left and right parts at $3 each, and two front and back parts of $2, we can say that left and right, with y and c involved, cost $6, bottom, with x and y involved, costs $5, and front and back, with x and c involved, only $4. Thus x is involved in the middle and cheap, c is in cheap and expensive, and y in middle and expensive. For this reason, one should not use much y, but a lot of x. Interestingly, the ratio of x to c to y is 6 to 5 to 4. Note that the costs were $3 twice, left and right, $5 for the bottom, and $2 twice again, front and back. So the numbers 6, 5 and 4 are echoed in the prices. I leave it to you to find out whether this is always the case in box problems like this. Alright, thanks for listening.